Hi, my name is Jonathan Zhang, and I am an electrical engineer, undergraduate at the University of Illinois. Today I will talk about radiation resistance and directivity of a Hertzian dipole. So, a Hertzian dipole is an infinitesimally long piece of wire, antenna wire, going from a negative charge to a positive charge with current varying omega t, which is dependent on frequency by 2 pi f. Now, since this is not on the Hertzian dipole itself, I will assume that you know what the electric and magnetic fields are for the Hertzian dipole. So for this case, we are going to assume that our point of interest is a distance r beyond the Hertzian dipole that is much larger than 1 over beta, or equivalently wavelength over 2 pi. So what does this mean? That means that the 1 over r term is small, because r is large, and 1 over r squared and 1 over r cubed and etc. terms become minuscule in comparison. So with that assumption, we can simplify our electric and magnetic fields to these values, where beta is dependent on wavelength, epsilon is dependent on our material medium. Now we are going to assume our coordinate axis of this, where our theta goes from the z-axis to our point of interest r, and our phi goes from the x-axis to our point of interest r. So, since we are far enough away, the Hertzian dipole is situated at the center, and it will radiate a sphere of radiation a distance r all around it. Alright, we know that the electric and magnetic fields are perpendicular to each other as well as the direction of propagation. And since, like we said before, there is uniform radiation of a sphere, the phase of the field is the same throughout. So we will now take the cross product of our electric and magnetic fields to find the pointing vector. And when we work out all the math and all the calculus, we get this expression. Now we have to remember that the differential surface area of a sphere is this. So we have our pointing vector. To find our radiation power, we want to take the total surface integral of our spherical surface. So using our surface area spherical surface, we take our integral with p as our pointing vector. So we plug in our pointing vector into p, take our integral. So this is after we plug it in. First we take our integral with respect to phi, then with respect to theta. And finally, we manipulate this expression a little algebraically to get this. So same expression, just manipulated it a little. Now this is our power radiated out of a Hertzian dipole, a distance r from the Hertzian dipole. That again is large enough that it's much greater than 1 over beta. So our total power radiated. Now from basic circuitry, we know that power equals voltage times current. We also know that power equals current squared times resistance. Now time average power equals 1/2 of that, so 1/2 current squared times resistance. So we now want to find the average power radiated. We know that the average of the sine term from our previous expression of power radiation, which is this, the sine term, when we take the average time, goes to 1/2. So we plug in 1/2 into our power radiated, and we get this expression, which is our average power radiated. Now, we want to manipulate this equation so it fits the form of power equals 1/2 I squared r. So we algebraically manipulate this expression into this. So nothing new has changed, just we moved around some terms. So we have 1/2 I squared r. Now this r becomes our radiation resistance of our Hertzian dipole. Radiation resistance. Now, how does this radiate? Well, if we look at the power radiated, we see that it depends on a sine term. So when theta equals 0 degrees, there is no power radiated. As you increase theta to 90 degrees, maximum power radiation is achieved. So in this case, the pattern becomes this, where the length of the arrow represents the magnitude. So this is similar. If we have a Hertzian dipole going from negative charge to positive charge, it will radiate like this with two oval-shaped circles of radiation. And that is our pattern. Again, because of our sine expression here. When theta goes to 0, we have 0 radiation. As theta goes to 90 degrees, we have max radiation. Now, our directivity is defined as our average power, our max power divided by our average power. Our max power from our pointing vector is this expression. So it's just from our pointing vector that we derived before. Now our average power is going to be our power radiated over the surface divided by the total surface area. So intuitively, it's the entire power divided by each infinitesimal length of surface area. So we have power radiated from before that we derived divided by 4 pi r squared for a spherical surface. And we get this expression. Now, when we divide this value by this value, which equals our directivity, everything cancels out perfectly and we get a constant of 1.5. So this is our directivity of a Hertzian dipole. Alright, now I'm going to put the more important slides here and the radiation patterns. And feel free to look at the previous slides and pause if I went too fast. So thank you for tuning in.